are going to do the second derivative test. And the second derivative test is about finding maximums and minimums, just like the first derivative test. But it's like, you know how we had the graph before? It's like pretending you didn't do the first derivative, or you just did part of the first derivative. I don't know why you would stop, right? It was like you found the critical points, but never did this number line with the first derivative test, decided not to find out where it's increasing and decreasing, but you wanted to do your second derivative right away and find out where things were concave up and concave down. And so if at -6 in our example where we found this point, if at -6 you know it's a critical point, but you don't know that it was increasing and decreasing, but you do know that it's concave down. Does it make sense that if it's concave down and a critical point, that it would have to be a maximum? That's the only way you could have a critical point and also maintain concave down. And that's what is said in these points here, that if it is concave down, and you know the first derivative is 0, second derivative is less than 0, so it's concave down, that makes it a local maximum. If it is concave up, and it's a critical point, the only possibility is it's a minimum. Here's the idea. Concave up, and it's a critical point, would have to be a minimum. Concave down, and a critical point, it would have to be a maximum. So the second derivative test doesn't come up very often, because usually you did the first derivative, and you did increasing and decreasing, you already know where the maximums and minimums are. That's what I think makes this tricky, because sometimes it comes up on the exam, and you haven't worked with it for a while. So, second derivative test is another way of finding maxes and mins that uses concavity. And it's very easy to confuse it with just finding concavity. So in this question it says, find the coordinates of the local max and the local min and the point of inflection, and use the second derivative test to show that they're maximums or minimums. So we could take our derivative and take our second derivative right away. We set our first derivative equal to 0. Factors out that 3 really easily, then you have a difference of squares. So you can find out your critical points are at 2 and -2. Now, it kind of bothers me because I really want to write that line and show increasing and decreasing at this point. I think it's a great strategy when graphing to always do that. But since we're focusing on the second derivative test, we're going to just move forward and skip that. Kind of bothers me, I have to admit. But to really focus on the second derivative test, we would say, well, if I plug in 2 into my original equation, I'm going to get -11. And if I plug in 2 into my second derivative, it's positive, happy Cyclops, concave up. And if it's concave up at that point, that's telling us that that point has to be a local minimum. For our second point, again, to find the y-coordinate of our second point, plug that -2 back into that original equation. And when I plug in -2 into the second derivative, it's negative concave down that face. But that means that we would have a local maximum. So normally, we would have done our first derivative test right after the first derivative, drawn our number line. Normally, you would go and draw your number line for the second derivative too to find concave up and concave down. But here, we're focusing on the second derivative test, so we're like, omitted that. Or it could be, maybe sometimes the second derivative test feels like it might be faster than the first derivative test. Not very often, but might be something that you would want to do instead. So now if we look at, here, I'll do the whole page. If we look at the graph, we have all of our points. We could find our point of inflection by setting our second derivative equal to 0. We get x is 0. Plug that 0 back into the original equation. So had we done that first derivative test, you would have had this number line here with f prime, and you would have plugged in -2 and 2, and you would have found positive increasing, negative decreasing, positive increasing. But that would have given away that the max and min were what they were, and then it would have taken away from the second derivative test. And because of this, the second derivative test isn't as well known, because most of the time you don't need to use it, because you've already figured it out with your first derivative. So I'd like you to try the next one on your own. I'll put the answer up in a bit. All right, I'll put up the answer and see how you're doing, if you're coming along. So again, I skipped the first derivative test, but we could definitely add it here. And you would have known, you would have seen that it was negative here, decreasing, negative still, decreasing, and then positive after increasing, which made 0, 0 a stationary point of inflection. I'm going to point out some things that you could also use from grade 12 in this one. I want to point out that you could have factored out an x cubed out of the original to give you x cubed times x minus 8. Can you see that if I did that, I would have gotten, wow, that's here.
Mr. Chair, do you have a class set of calculators I could steal, like just graph normal ones, scientific?
Yep. Not a class, but a pen. Pen enough.
Thank you.
So do you see you could get that x-intercept by factoring? Do you remember from grade 12? When we talked about multiplicity of a 0, that it has a multiplicity of 3. So that rings a bell. And when it had a multiplicity If it was even, it bounced off the x-intercept. And if it was odd and bigger than, like if it was odd and it was 1, it went straight through. And if it was odd and bigger than 1, the graph bent. Now that bend, we now know as a stationary point of inflection. Because it flattens out and bends. It flattens out so that you have that critical point, the tangent is 0 at that point, and the bend is the fact that it's changing concavity at that point. So it's kind of neat to see how they couldn't teach you about concavity and inflection points and tangents of 0 stationary points in grade 12. So they kind of like pointed out some of the ideas that were coming up in a different way. But it's kind of neat that you could still use, if you see that, you'd be like, oh, it's going to be an inflection point there.